Welcome back to our pre-recorded lecture series. So this is lecture, and I'm going to have a new system, lecture 2.1. So this is the first part of lecture 2. So this one is really going to be on basic concepts of thermal physics. All right, so the first concept that we really need to think about in thermal physics is that of the system, okay? And by system, what we really mean is that part of the universe that we are focused on. Okay, that seems very simple, but one of the keys is that it's actually separated from its surroundings by some sort of boundary. Okay, so we're going to think a lot about these boundaries in this class, and we're going to have various kinds of boundaries. So for example, your boundary could be open or closed. So what do I mean by that? I mean, by open, I mean that you can exchange with surroundings. And by closed, what I mean is you cannot. You cannot exchange energy or matter, right? So a boundary could have different aspects. It could be able to exchange energy, but not matter, for example. So you could have something that could allow some form of mechanical energy to pass through, but not have matter to pass through. Or you could have matter pass through, but not energy, for example. So we'll have to think about, well, maybe you can't do that. We'll have to think about that. That probably isn't possible. All right. Just making sure my mic is actually on. All right, so one possibility here, you could think about thermally insulating boundaries or walls. So I'm going to probably call them walls more often than I call them boundaries. So what's a thermally insulating wall that you know of? Well, actually, styrofoam is a particularly excellent thermal insulator. Right? So you can have say a beer cooler that you take camping with you this summer, right? And you can actually have the styrofoam provides an excellent thermal insulator. Another example of this is your coffee cup. So a coffee cup is called a thermos, which is just made up from the word thermal, of course, but the proper word for that is a dewar. So a dewar is this vacuum insulated container. So I have a lot of different kinds of dewars in my lab, and actually what I'm hoping to do is, if I can figure out how to do this video editing, slice in some pictures from my lab right here at this point in the video. Now, sometimes we're going to call these adiabatic walls. So So this kind of wall, a thermally insulating, we might call adiabatic or diathermal. Okay, so you can see the root there of those words is dia. That means through in Greek, right? So this one means it's adiabatic. It doesn't actually exchange energy, and diathermal means it does allow thermal. It doesn't allow thermal energy to pass through. Sorry, diathermal. Sorry, let me say that again. Adiabatic means no heat transfer, right? Or actually, it really means no change, really. And diathermal means it allows heat transfer. In this context, we really mean no heat transfer when we'll say in an adiabatic wall. Okay. Now you can compare that, for example, versus what we'll often call rigid walls, right? So you could imagine having a styrofoam membrane that's thin enough that it flexes, right, and allows some non-rigidity, some mechanical energy to pass through, but no heat transfer. So how could you have a system? So let's imagine another system, a system that allows no heat. So it's going to be adiabatic, but is not rigid. How would I compose a system to do that? Feel free to pause and take a second here to think about how you might actually make that, right? So one way you could do that, for example, is imagine making a piston, right? So imagine these being adiabatic walls that don't allow any heat to pass through. So for example, like a styrofoam or a glass dewar. And you could actually imagine having another adiabatic wall here, but that is a piston which is movable. Right? And if you applied a force to this, that would move. So it was non-rigid walls, right, between the system, right, and its surroundings. Where these were the adiabatic walls, but this was a movable wall. Great. So So one of the important concepts that we have, for example, is if I were to take this system as an example and move that piston, right, now my system is out of equilibrium, right? So if you disturb a system, it'll go out of equilibrium, and you need to wait long enough to regain equilibrium. So how do you know that you've regained equilibrium? Okay, so that's the question. So you need to wait long enough that the properties of the system, that is that part you're focused on, right? Your surroundings may no longer be in equilibrium, but the properties of your system are now static, right? So they're not changing. So that is, they don't change with time. and properties of your system are homogeneous. That is, they're uniform, right? If you have any kind of gradient, so for example, here you could have a density gradient, or you could have a pressure gradient, or you could have a thermal gradient. If you have any gradient in the system, any non-uniformity, your system is not in equilibrium. Okay? Now, one of the great things about an equilibrium is that it only takes a few, we're going to call them thermodynamic variables. So this is a key term. Only a few thermodynamic variables to define a system in equilibrium. So a few examples of these thermodynamic variables are pressure, temperature, volume, and mass, or number of moles. Now, a couple of important points about these thermodynamic variables. So the first point is about units. We always prefer SI units. All right, so, but often you will need to convert. All right, our neighbor to the south does not use SI units often, so we will often have to convert, for example. So you might be given a pressure in PSI, right? That means pounds per square inch. So pounds and inches are neither. But you might also be given, for example, so this is a good example, pressure. So pressure is defined as the force per unit area. So we're going to cover this again in lecture 2.2. Right, we're going to go into more about that. But the SI unit for pressure, the SI unit of pressure is the Newton, because that's the SI unit of force, per meter squared, because meter is the SI unit of length or distance. Okay? So a Newton per meter squared is called a Pascal, written as PA. So that's a Pascal. Okay. But you might, for example, have been given, in PSI, ATMs, that's atmospheres, bar, torr, millitorr, there's a huge number of units, right? Likewise, as a low temperature physicist, I always prefer the SI unit of temperature, which is the Kelvin. But often, we think in, Celsius. We think in Celsius when it's the weather outside, but we think in Fahrenheit when we bake, right? No one says, turn on your oven to 100 degrees C. They say, turn it on to 450 Fahrenheit. All right, so maybe those are the correct adjustments. I don't know. Full disclosure, I'm an American, but I have lived in Canada for more than 12 years now. So this is my home. Now, the second point I want to make about these thermodynamic variables 2. And the second point I want to make about these thermodynamic variables is that there's 2 types. There's so-called intrinsic variables and extrinsic. Okay, so this is an important concept and you're going to have to remember this. So intrinsic variables do not depend on system size. And extrinsic variables depend on system size. Okay, so because this is a pre-recorded lecture, the so-called asynchronous, if you have any questions during the lecture, pause it and send me an email. That's jdavis@ualberta.ca. Send me an email and I can try to answer your questions, or you can wait till class time and ask them there. All right, so what do I mean by doesn't depend on system size? I mean, for example, let's say I take my system and I double it, okay? So I imagine just having twice as much. So I have 1 liter of water, and then I add another liter of water to my jug, and now I have 2 liters of water, okay? So do these variables depend on system size? Okay, so let's take the first one, pressure. Okay. If I have a certain volume of air in the room and I double the volume of air in the room, do I change the pressure? Hopefully you answered no. So pressure is an intrinsic variable. It doesn't matter how much of it I have. Similarly, temperature. If I take a system and then I double it, do I have twice the temperature? No. Right? So temperature is also an intrinsic variable. How about volume? If I take a system and I double the volume, do I change the volume? Aha, of course. Volume does change with system size. And for example, mass. Obviously, if I double the volume of a system, if I have twice as much of the water in the jug, I have twice as much mass, right? All right. Okay, but an interesting point is that I can make an extrinsic variable. Let's put a lowercase e there. Let's make an extrinsic variable intrinsic by dividing by a second extrinsic variable. Okay, that's actually easier than it sounds. Let me give you an example. Let's take the volume, it's an extrinsic variable, and let's divide by the mass, so also an extrinsic variable. And what do I get? I get the density, okay? But you can see density is something that is intrinsic, right? The density does not depend on system size. All right, so that's lecture 2.1. So next we're going to go on to lecture 2.2, and we're going to think a little bit more about pressure.